So when we see the big O notation, big O notation is a way of comparing algorithm and is used for computing the complexity of an algorithm. It is only concerned with what happened for very large value of n. Therefore, only the largest term in the expression or the function is needed. For example, if the number of operations in an algorithm is n squared minus 1, n is insignificant compared to n squared for large value of n. Hence, n term is ignored. Of course, for small one value of n, it may be important. However, big O is mainly concerned with large value of n. When we see the formal definitions of big O notation, so f of n which is equal to big O of g of n if there exists c and n naught. It is subset of positive constants such as for all n greater than n naught, f of n less or equal to c of g of n. This is the definitions of big O notation. So based on this definition, let's see some examples, like if the time complexity or f of n which is equal to 10n plus 5 and g of n which is equal to n shows that f of n is big of g of n. Let's see the above example in detail. So 10n f of n which is equal to 10n plus 5, right? 10n plus 5. So let's show that f of n is equal to big of n. Let's show that this one. So to do this, when we see the definitions of big O notation, f of n less or equal to c of g of n. So 10n plus 5 less or equal to c of g of n, right? So here we can simply add any function that should be greater than this function, right? This function. So 10n plus 5 less or equal to, let's try to add the function that is greater than this one. That's greater than this function, right? So we can add 10n plus 10n plus 5n, 10n plus 5n, right? Then 10n plus 5n less or equal to 15n, right? 15n. So this is always true when the value of n greater than 1, right? Greater or equal to 1. So when we replace 1 at the value of n, so 10 plus 5 which is equal to 50 less or equal to 50. That is true. When we add the value of n is 2, it is obviously greater than this one. So this 15 is the value of c, and this n is the value of what? G of n. G of n. So this is f of x, f of n. So f of n which is equal to, which means in general we can say that f of n which is equal to big of Joffre, right? In the definition. In the definition, there is f of n which equal to big of Joffre. So which equal to big of, add the value of Joffre. Joffre means n right here. So n. So f of n which equal to big of Joffre. So we can do just like this. Let's see another example. 3n square plus 4n plus 1. 3n square plus 4n plus 1. So 3n square plus 4n plus 1. 3n square plus 4n plus 1. Plus 1. So let's show that f of n which equal to big of, big of n square. Let's show that f of n which equal to big of n square. So we simply use the formula of big O notation. So f of n, 3n square plus 4n plus 1 less or equal to c of c times Joffre, right? C times Joffre. So which means we will add any function. Actually, there is no a formula to do this, but we will use try and error methods. So 3n square plus 4n plus 1 is equal to any function. So any function that's greater than this one can be used here. So simple, to make simple, we can use this constant, this function constant, and the highest power. So 3n square plus 4n square plus 1n square, 1n square. Actually, we have to use the single term here. We can't use multiple terms here. So we use n square only. So less or equal to 3n square plus 4n square plus 1n square. 7n square plus 1, 8n square. So less or equal to 8n square. Which means 3n square less or equal to 3n square plus 4n plus 1 less or equal to 8n square, right? When this will be true when the value of n greater or equal to 1, greater or equal to 1. So we can check by replacing the value of n here more than 1 value. So this means this one is the f of n, and this one is, this 8 is c, right? And this one is Joffre by using this formula. So which means f of n which equal to, we can define f of n which equal to big of Joffre. There is here, right, in the formula of big of notation, which means which equal to big of, what is the value of Joffre? Joffre is n square. So f of n which equal to big of n square. When the value of n is should greater than or equal to 1, and the value of c is what? The value of c is 8. So we can simply prove any time complexity for any algorithm just like this. So we can represent this time complexity class, or this time complexity class is belongs to n square. It is belongs to n square. Okay, this is how we use big O notations. Actually, there is a theorem for all the following theorems. Assume that f of n is the function of n and that k is an arbitrary constant. So the first theorem is k is big of n. If k is constant, then big O notation of k is big of 1. The second theorem is a polynomial is big of the term containing the highest power of n. For example, if we consider the previous one, 3n squared plus 4n plus 1, right? So this one, n squared is the highest power of, contains the highest power of n. So we will consider this one only. So polynomial growth rate is determined by the leading term. If f of n is polynomial of degree d, then f of n is big of n the power of d. In general, f of n is the big O of the dominant terms of f of n. Theorem 3, k times f of n is big of f of n. Constant factor may be ignored. It is not considered if there is a constant. For example, 7n the power of 4 plus 3n squared plus 5n plus 1000 is big of n the power of 4. When we see theorem 4, for any base b, log b of n is big of log n. So we simply ignore the base. All logarithms grow at the same rate. So we will consider, we will not consider the base one.